Okay, dynamics. Let's look at what the impulse method looks like for rotational motion for solid objects. All right. For first, let's review the or the linear impulse momentum. We start with F equals ma. Write acceleration as dv dt. Integrate both sides, and we declare this left side, the integral of f dt, we just give that a name and call that impulse, j. And then on the right-hand side, after we integrate both sides with respect to time, we just get m times the integral of dv. The integral of dv is v. And when you put in your limits from v1 to v2, you just get the change in velocity. So impulse is mass times the change in velocity. Now, how about we start with our angular momentum equals sum of the moments equation. So the sum of the moments acting on an object equals h dot, means the rate of change of its angular momentum. So I'm going to drop the summation symbol just the same way we did over here. I dropped the, of course that F meant the sum of all the forces. So here this moment means the sum of all the moments equals dh dt. Integrate both sides with respect to time, and the integral of dh dt with respect to time is just dh. Integral of dh is h from your initial to final angular momentum, which is your change in h, just like it was change in velocity over here. And on the left-hand side, we've just got the integral of m dt. And I'm going to leave this equation in that format. Okay, now let's go ahead and use this. So I've got a sample problem. And in fact, I've got two sample problems. The first sample problem is going to be, so I'm going to do two problems side by side. I'm going to do one that involves linear impulse and momentum on the right, and at the same time, I'm going to do one that involves angular momentum on the left. Okay, so on the problem on the right, I've got a block that's initially moving at 5 meters per second to the right. The coefficient of friction is 0.2. And I want to find the time it's going to take to stop. Okay? That's the linear problem. That's the problem we already know how to do. Compare that to this one. I've got a disk rotating. So it's rotating at 5 radians per second. It's got some mass. And I'm going to apply a force that slows it down, some frictional force. And in this case, the way I'm going to apply that force is I'm going to have this beam here, and there's 10 newtons pushing down on the end of the beam. And if you do a little statics on that, because that beam itself is not moving, it's not accelerating, you can find the force of it pushing down on the wheel to be 14.3 newtons. So I've got some, and as it slides, there'll be a force of friction opposing the motion of the disk equal to mu times the normal force. And since the normal force is 14.3, and because I love 0.2 as my coefficient of friction, that force would be 0.2 times 14.3, which is 2.85. Anyway, in both cases, there's an object that's moving, and on the right side, in this case, the object is translating, which is our word for moving but not rotating, and on the left side the object is rotating but not translating. Okay, and in both cases we're going to be slowing it down, and in both cases I want to find out, so in this case also I want to find the time it takes the disk to stop rotating. So we're asking the same question in both cases. Okay, so in the right-hand side, we would use impulse equals change in momentum. Our change in momentum, our final momentum is 0 because it's come to a stop, minus the initial momentum, which is mass times velocity, so mass times 5 meters per second. And on the left side, the impulse, of course, by definition, is the integral of f dt. In this case, the f is a constant, so it can come outside the integral. That force is mu times the normal force, and in this case, the normal force is mg. So you get the force, which is a constant, times the integral of dt. Integral of dt is t. So we have t times 0.2 mg equals mass times 5. Because the force of friction is to the left, see here the force of friction is to the left, then this has a minus sign, and this has a minus sign because of that minus sign. So the minus signs cancel, and we get a time of 2.55 seconds. Okay, let's look now at the example on the left. Okay, very similar, very similar. Even the equations look very similar. So the change in angular momentum, what ends up being stopped, so that's a 0. Oh boy. Okay, and the initial angular momentum you found out in the last video for a solid object rotating in 2 dimensions, or well, in planar rotation, is I times omega if you're calculating it about its center of mass. So we take the final angular momentum, subtract off the initial angular momentum. Note, though, that in my problem, the omega is negative. That 5 radians per second is rotating clockwise, which is negative. So in the negative k-hat direction. But the negative there and the negative there combine to make a positive sign. The moment of inertia of a disk is 1/2 mr squared. And finally, our omega is, we just plug in a 5 radians per second. Okay, on the other side of the equation, it's the moment, and in this case, the moment, slowing it down, is a constant, so it can come outside the integral. That moment is force times distance, so it's the 2.85 times r, and that moment is positive. Integral of dt is t. Bring this r down to the other side and solve for t, and we get 2.92 seconds, and that's using an R of 3 meters. Can we do a quick unit check on this? I think so, but we have to kind of untangle some of these numbers. Basically what we're saying is the time is I, remember we know the units of that, times omega divided by a force of friction times R. Okay, so let's see, does that check out unit-wise? Well, the units of I would be, let's do this in a different color. This would be kilograms meters squared, and omega is radians per second. Force is kilogram meter per second squared, and R is meters. So the per second squared in the denominator comes up to the numerator. This all cancels out, and we get seconds squared divided by seconds, which is seconds. All right, so the units all check out there for the 2.9.